In this lecture, we will analyze Class A power amplifier. So first we will see the circuit of Class A power amplifier, and then we will carry out the analysis for the drain efficiency. So we are going to first see the simplest implementation. So this is the simplest possible scenario for Class A. Later on, we will add the LC network here on the output side that we have shown in the previous class, but we are for moment neglecting it. So this simplest circuit is used when we assume that Vi is small. So recall the previous lecture analysis. This implied that Vi square is negligible. So in this case, we were able to neglect the square of the input. When you include this Vi square, then there will be second harmonic also. So since we have neglected, this circuit is enough. And later on, we will once we include it, we will have to put this LC network also to mitigate the effect of the second harmonic. So here we have simplest version, and as was pointed out at the gate, we have two inputs. One is DC, so the total voltage VGS, which will be of course time varying, will contain two parts. The DC part, which is used for biasing the MOS, and the time varying part, which we will be calling as AC, or it can also be called as the RF part. So this is the story at the gate, and this VI is of cosine form with amplitude equal to A. So here we have a scenario at the input, and we have seen that in the last class that this DC give rise to one DC current. So there will be, here we will have total drain current ID, and this total drain current will also have two parts, ID, and this will be function of VGS. In fact, we had derived it, and there will be time varying drain current, which will be a function of the input. So there will be two components to the drain current, DC and AC. AC is actually the RF part in which we are interested. So now we would like to see that how these two components of the drain current, they are going to flow. So for that, here we will point out the impedance offered by RFC and by this uh, blocking capacitor. So at high frequency, at which is RF, at RF, omega is high, therefore RFC, whose reactance is going to be omega L, in fact J omega L, is going to be very high, and hence this will act like open circuit. While CB, the reactance offered is going to be J omega CB, and this is going to be very low. So this one will be acting like short circuit, right? So here we see that total drain current has two components, DC and time varying. So what will happen is the total drain current will flow uh, through two different paths. So for DC part, we will have this condition. So we see that for DC, this circuit will reduce to this equivalent circuit. So the drain DC part of the drain current is going to flow like this. Of course, here we will have load. And for AC part, scenario is going to be different. So in this case, the RFC will be like open circuit, and this blocking capacitor, this one will be like short circuit. So load is now connected to the MOS, or in fact the drain of the MOS. So we see that the time varying drain current is going to take this path. So finding the equivalent circuit and more specifically the path for different component of drain current is important. This we will be carrying out for all the subsequent power amplifiers, and this will allow us to find the drain efficiency. Okay, so here we see that in the DC equivalent circuit, so this drain is now short circuited to VDD. So this immediately implies that there will always be DC voltage at the drain, and this DC voltage is always going to be equal to VDD. So this is one important conclusion from this equivalent circuit. Now from the AC we find that there is going to be certain output voltage at the drain because of the ID flowing through this RL. And typically we will be calling this as drain voltage, time varying drain voltage. And here we will be calling as output voltage, and both are actually exactly same. And here we can see that this time varying drain voltage that we will see will be equal to minus RL into ID. So these two equations are very important. We will be using them very frequently in our analysis. So as was pointed out, our objective is to find the drain efficiency. And this eta D was defined as power, RF power to the load divided by DC power from VDD. So our objective is to find PL and PDC. So once we know this, we know the efficiency, and then we will try to see if it is possible to maximize it under suitable condition of the input. Okay. So what we took for the input was so this is the time varying input, and total VGS we had already found out. Here, and drain current also we had found out. So now we are going to plot these waveforms and then see that what will be PL and what will be PDC, and then try to possibly maximize it also. So we are, since we are considering the class A, so for class A, this VGS is greater than the amplitude of the input, so that net gate to source voltage for the circuit is always positive. That means there will always be drain current. So this implies VGS is always greater than 0. This implies that ID will always be non-zero. So now let us see the waveforms for these cases. So let us assume this is the bias gate to source voltage, and what we are plotting here is total gate to source voltage, and this is the zero line, this is time axis. So on this gate to source, we will have a time varying cosine function oscillating about this line. So what we will be having is something like this. Here. So this is Vi, and the amplitude is A. This is also A. And here you can see that VGS is greater than A. A is smaller than VGS. This much is VGS. So this now is going to give rise to drain current, which will also have time varying and DC part. So this is the total drain current, and there will be certain DC drain current, and on this we will have our time varying drain current. So this one is time varying part of the drain current, and it is going to have amplitude, which we will be designating as IP. Now it is this drain current, time varying drain current, which flows through the resistor to give rise to uh, output voltage. So this VGS is, sorry, not this one. The output voltage or the total drain voltage is going to be equal to VDD. We have already seen from the DC equivalent circuit, plus the output or the This is total drain equal to DC plus output, or VDD plus VD, and VD is equal to minus RL ID. So here we see that the drain voltage will also have a DC voltage and AC, and this AC one is going to have a 180-degree phase shift with respect to ID. So now if we plot the drain voltage, this is a total drain voltage. So here also we will have a DC equal to VDD, and then this AC part, and this is having phase opposite to that of the drain current. And we know that common source or common emitter amplifier, they give voltage which is 180-degree phase shifted with respect to the input. So here you can see that input and output, they have 180-degree phase shift. Now this is going to be the amplitude of the output. And in general, this might be smaller than VDD. So these are the three waveforms, important waveforms for the class A power amplifier. Now we will use this to find out PL and PDC. So here, so PDC is going to be equal to the DC power that is being drawn from the circuit. So that is going to be equal to this DC voltage multiplied by the DC current that is being drawn. So this is going to be equal to VDD into ID. And keep in mind that this ID, what we get here, is actually function of VGS, the gate to source voltage that was used for biasing. So this information will be useful later on. Actually, in this circuit, the class power amplifier, there are three independent parameters, and they are VDD, VGS, and the amplitude of the input. We can choose each of these three independently, and they will have consequences on the efficiency. We will see it soon. Now, second power that we want to know is RF power to the load. So RF power to the load is actually going to get determined by this voltage waveform, or by this time varying drain current waveform, because we saw that it is actually this drain current which flows through the load here. So the RF power to the load will be determined either by this voltage or by this current. So it can be written in form of any of these two quantities. So let us write this in terms of, say, IP, in terms of this ID, and whose amplitude is IP. So this ID is IP cos omega t. So in terms of this drain current, we can write IP square RL by 2. Since we are considering the amplitude, so that is why we have 1 by 2 factor in the denominator. This is not the RMS value, this is the peak value. And keep in mind that this IP will be related with the peak voltage. Let us call this simply VP, the amplitude of the output VP. And this VP and IP, they are going to be related via this equation. That is the load equation. So this VP is going to be minus RL IP. So now we have these two quantities, equation 1 and equation 2. So we can find out the efficiency eta D, and this is going to be equal to PL divided by PDC. This is going to be IP square RL divided by 2 into VDD into ID. So this can be rewritten by separating out the quantities which can be varied with the help of one of the three independent parameters that we just pointed out. So I have separated out VDD, although VDD can also be varied. So RL is certainly fixed, and so this is the only fixed parameter. And for the moment, we will assume VDD also to be fixed, and we will play only with VGS and A. These two are the input quantities on the input side, bias and the amplitude. Right. So here we see that we have in the numerator quantity, current quantity, which is determined by the amplitude of the input. So this IP amplitude, this amplitude is going to be decided by this amplitude of the input. So if we have a larger A, IP is also going to be larger. So this is one thing. Second is, if we increase this VGS, then this ID is also going to increase. So ID is function of VGS, while IP is function of amplitude A. So here in this case, we find this scenario. Right. So this is the general formula. Eta D, we see that depends upon the amplitude, depends upon VGS, and in fact, it also depends upon VDD. So in general, this is going to be the efficiency. Now we would like to see that under which condition this can be increased. So there is a scope of increment here, because IP can be increased, this numerator, by increasing A. So here we see that we have this waveform for the IP or ID. IP is actually the amplitude of the ID. So here we see that we still have a room for the growth. That means IP can be further increased by this much amount, right? So that means if I increase A, so this IP is also going to increase. That means we will now have a waveform that is going to be something like this here, almost touching the this zero line. Shown it slightly wrongly, like this. So by simply increasing the A, we will be able to increase IP. That means we will be able to increase this. You increase A, this IP goes up. That means your eta D goes up. And this can be done without altering, keep in mind, VGS or VDD, right? So so for increasing eta D, first what we do is increase the amplitude. So we increase the A, so this increases IP, and this will increase the efficiency. Now the question comes that what is the maximum extent to which this IP can be increased? So of course it can be increased up to this range, and this range is ID. So we can increase our input amplitude to such a level so that the drain current swing becomes maximum equal to ID, the DC current that is being drawn. So here, keep in mind that for fixed, we haven't altered VGS and also VDD. The IP max that we can get is equal to ID, right? So we simply increase the input, IP increases, it becomes equal to ID, and then we have a slightly increased eta D, and this eta D is going to be given by ID square by, now in place of IP, we write ID divided by ID into RL divided by 2 VDD. So this becomes equal to ID RL divided by 2 VDD. So we can give it a slightly different name, ID1. So ID eta D1 is greater than eta D, the previous eta D that we obtained here in equation 3. Right. So now we have the drain current of amplitude equal to ID. This flows through RL and then produces this VP. So when we have increased our IP, this output voltage is also going to increase. But we still do not know whether this increase is also going to be this much, the full range available for the growth of the drain voltage, or it could be smaller or it could be larger also. So we will discuss this part later. So, but what important thing we have here is that this ID RL is going to be equal to VP, and VP is the swing of the output voltage. And this VP need not be at this moment equal to VDD. There is no guarantee that this is going to be the case. So we can now substitute this equation in the previous. So we get eta D1 equal to VP divided by 2 VDD RL. Sorry, no, RL will no longer be there. So here what we have 1 by 2 into VP by VDD. So we still see that there is still room for changing eta D1, because now there are 3 possibilities for VP. Case 1 is the simplest case, and these 3 cases arise when we have increased the input amplitude to such a level that drain current swing is the maximum possible for chosen value of the gate to source voltage. So now there is no room of further increasing the drain current swing because gate to source voltage is fixed. So under this scenario, now there are 3 possibilities for this VP waveform. One is that this VP is actually also equal to the full range possible. That means equal to VDD. That is the first possibility. Second possibility is it is less than VDD. Third possibility is it is greater than VDD. So we'll consider all these 3 cases. So first is VP is also equal to VDD. So we have such a scenario. So in this case, you can see that eta D1 is actually going to be the eta D maximum because and it is going to be 1 by 2. So this is going to be the maximum value. I pointed out that VP could be greater than VDD, but there is a problem that actually will not happen in real life. So what will happen is VP will always be less than equal to VDD, and we will talk about why this we have scenario like this. So this is the ideal case. Second is VP is less than VDD. So if we have this scenario, then we will have to do something else to further increase. So now here you can see that VP is less than VDD. So obviously now the eta D is going to be less than, implies that eta D1 is less than 1 by 2. So obviously this is less than the eta D max that we got in the case 1. So then how to further increase this eta D1 so that it becomes equal to 1 by 2. So for that, we will have to make changes. So you see that we have to increase VP to the extent equal to VDD. And this VP is IP magnitude wise RL. Minus sign is there, but we are talking about only the magnitude. So if we want to increase this VP, we will have to increase IP. So only when we increase IP, VP will increase and it will become possibly equal to VDD. So now if we want to increase this IP, we will have to increase the input amplitude because IP is determined by IDD. And we have already reached scenario when IP is equal to ID, the maximum swing possible. That means in this scenario, when VP is less than VDD, we simply cannot increase the input amplitude to increase the output swing to maximum possible equal to VDD. So what else we will have to do? We have to now increase the ID value itself. That means, so we will have to increase VGS. That will increase the DC value to something like this. So this is going to be now new ID, let us say ID dash, and this ID dash is greater than the previous ID because now VGS is larger than the previous case. So once we have increased ID, now there will be room, this much room for the growth of IP. So now we will go back to increasing the amplitude of the input. So we increase the input amplitude till it becomes sufficiently large so that VP is equal to VDD, right? So in this scenario, when VP is less than VDD, we will have to change both VGS and the input amplitude in such a way that VP becomes equal to VDD. So what is going to be the sequence of change? So for this case, you increase VGS, this will imply increase in the maximum drain current swing, and this, not this implies, then you increase A, so this will imply increase in IP, and this will then imply increase in VP, since VP is equal to IP into RL. So now we will have to make these two modifications so that this VP, which is less than VDD, ultimately becomes equal, such that VP finally becomes equal to VDD. So once VP becomes VDD, what we got here eta d1 less than 1 by 2, this will become 1 by 2. So eta d1 will now also become 1 by 2. That means eta d max value possible. Right. So this is about the two cases when VP is either equal to VDD or VP is less than VDD. So what we get is the maximum value of drain efficiency is equal to 1 by 2. That means equal to 50%. So this is for class A. Right. Now there will be one question that what if for any given IP, suppose we have maximized the drain current swing to IP such that the numerical value of IP into RL is greater than VDD. So we consider two cases initially, VP equal to VDD and VP less than VDD. So equal to, and this is less than. Now what about this third case? So here what will happen is if IP into RL is greater than VDD, then there is going to be distortion in the output waveform. Now the output waveform is going to be something like this. So suppose this is the VDD level. Now we are considering scenario when IP into RL is greater than VDD. So we are plotting this voltage or you can say this is also VDS. Since source is grounded, so that's why we did not include the S word. So this is in a way DS voltage. So here we see that the minimum value possible for this drain voltage is 0. And that is why we have y-axis starting from this 0 level. So if this scenario occurs, then we are going to get a waveform which will be flat at the bottom, slightly flat. Like this. But for the upper swing, it will be undistorted here. So we see that if this scenario occurs, then output waveform, and this is actually the output waveform, the waveform that load will see, there is going to be a distorted version. So that is why I pointed out in the very beginning that the circuit that we considered, let me replot this circuit here. This circuit was for the simpler case. Now, if we have this scenario, then we will have to modify this circuit. And in this case, we will have to include parallel LC network as well to filter out the higher harmonics that exist in this waveform. So this waveform will have various components. It will have DC and it will have first harmonic or the fundamental and then higher one. So what we do here is this fundamental is the signal which we want to flow through the load, and we calculate the RF power or the load power for this fundamental one. And this L and C, they are designed in such a way that they block the flow of the fundamental in this direction. So fundamental is actually pushed to the load. So first harmonic flows like this. So what we will see ultimately, even in this case with this parallel tank circuit, is that the output waveform is actually going to be like this, a pure sinusoid. So this is output with LC, and what we showed earlier, this is output without LC, black one. So there is a possibility of this scenario occurring. So that is why it is safer to use this LC network also. But if one can avoid this, then this can be excluded LC. But including LC is also required, because it was pointed out that for only for small VI, we found that the total drain current contain DC part and GM into VI, and it is this part which we call the AC component or the RF component. If VI is not small, then we will have IDC plus VI square K into VI square plus GM VI. So this is going to give rise to second harmonic, and of course a DC component. So if VI is large, then this will be there. That means this is also going to be there. So to filter out this, we again need parallel LC circuit. So the two regions why even for the class A this LC should be included is first is that in case input amplitude is such that output swing is larger than the given by IP into RL, larger than VDD. So to filter out higher harmonics in this case, and second is for large VI. In fact, for the majority of the cases, this input is going to be large. So it is better to include LC in the class A implementation also. Okay. So what we found is that the maximum efficiency for class A that can be obtained is equal to 50%. But for to attain this maximum efficiency, we will have to choose a suitable value of for eta D max. There will be suitable value of VGS and the input amplitude. And we will have to maintain this two parameter constant if you want this efficiency to be constant throughout the operation. But for AM signal, amplitude modulated signal, we know that A is variable, right? So we know that for amplitude modulated signal, A itself is going to vary. So this is A. So A is no longer going to be that value for which we got the maximum efficiency. And as the time passes, the amplitude of the input signal is going to be smaller and smaller. So what we will get is now the eta D will vary with time for AM signal. So the average efficiency for AM signal offered by class A power amplifier is going to be significantly smaller than the maximum value of 50%. So for AM signal, this is not going to perform quite well. Now let us talk about the device stress. That means when this is used, then what is the maximum voltage and current that it experiences, and then what is the output power capability. So we want to know the device stress. That means we want to know the maximum value of this drain voltage and the maximum value of the drain current that this device will experience. So for that, we will have to see those waveform that we analyzed earlier, plotted earlier. So we found that the maximum drain voltage that it experiences, the maximum swing from the lower to higher. So the maximum amplitude is equal to VDD. So total swing is going to be equal to 2 VD. So this is going to be the maximum swing experienced by the MOS for the drain voltage. Similarly, if you see the maximum drain current swing, then this is going to be equal to 2ID. So while designing this amplifier, one will have to choose suitable MOSFET which will be able to tolerate this swing in the voltage and the current. And power to the load, we had already calculated, and its maximum value is going to be when this Vp is maximum, which is equal to VDD. Now, therefore, the output power capability which earlier we designated as PN, but sometimes it is also designated as CP, is PRF or PL maximum divided by maximum voltage stress, this VD max and ID max. So this will turn out to be VDD square by 2RL divided by 2 VDD into 2 ID. So this is going to be equal to 1 by 8 VDD by ID RL. And for the maximum efficiency, we saw that IDRL is equal to VDD. For eta D max case, this PN or CP is 1 by 8. So this is equal to 0.125. So this number should be larger. Now we would like to see that what is the power dissipation in the MOS, because efficiency is quite closely related with this. Higher efficiency means less power dissipation in the MOS. So to find out that, we just need to find what is the product of drain voltage and the drain current. These two quantities we have to find out. So instantaneous drain voltage, this is of course going to be time varying VDD plus this VD, and ID is also time varying, and this is equal to the DC current and time varying drain current. So therefore, instantaneous power dissipation EMOS is going to be this VD into ID. Yeah. And we know that this drain voltage is minus RL into the drain current flowing through it. And this drain current is of cosine form IP into same form as the VI, the input voltage. Yeah. Right. So we can now take this VDD and ID common. So we get 1 minus RL IP by VDD and 1 plus A. Sorry, this is not A, rather IP. A is the amplitude of the input. So in general, this is going to be the power dissipated in the MOS. But we will be operating our amplifier for the maximum efficiency. So for eta D max case, so we had already seen that current swing IP is going to be maximum, and that implies RL ID. This is also going to be equal to VDD. So both voltage and current, they should swing to the maximum value. So now for this case, we will have this expression. So this will simplify to VDD ID into 1 minus cos square omega t. And we can expand this. So this will become 1 by 2 VDD ID into 1 minus cos 2 omega t. So keep in mind, this is the instantaneous power consumed by the MOS when it is being operated for the maximum efficiency. Now, if you find the average value, then we will have to find the average of this over one time period. So when we find the average of this, we see that the average of this part is going to be as it is, but the average of this is going to be 0. So what will happen is this will be simply equal to 1 by 2 VDD ID. But now if we plot this instantaneous power with respect to the other waveform, those waveform that we plotted, then we can see that we are going to have this behavior. So for example, this is the input waveform. In fact, it will be better to see the drain waveform and the drain current. So this is the drain voltage, and similarly we have drain current, because instantaneous power is actually product of these two waveforms. Yeah. So this quantity is product of these two waveform P, M, T is VD into ID. So here you can see that we are going to have a minimum value whenever either drain current is minimum, that means at this moment, or whenever drain voltage is minimum, that means at this moment. So when you multiply and plot it, we are going to get a power waveform like this. So there will be certain power, DC power, that is the P average in fact, and about this we will now have a waveform whose period is going to be half of the period of these voltage and current waveforms. Like this. So this is the PM max. So the basic idea of maximizing the efficiency is making these dips to be as low as possible. So here, because you can see that the current and the voltage, they are not swinging to the maximum value of VDD and ID. So that is why we are not getting 0 here at the lower portion of the power waveform. But when this voltage and current, they are made to undergo maximum swing, then this power waveform, this will come down. So it will be like this. Will be touching to 0. In this case, the power consumption in the MOS is going to be minimum. So the key idea of maximizing efficiency is to keep this product as small as possible or minimum. And this is what we try to do in all the linear class amplifiers, or even in the switch based power amplifiers.